Welcome to all dear students. In this class, we will discuss about the new chapter. In part B, the first chapter is application of AC circuits. See, in this chapter, so you have to discuss AC bridges. In AC bridges, there are three bridges: Anderson's bridge, Maxwell's induction bridge, Desart's bridge, and numerical problems. See, in application of AC circuits, so before going to understand the AC bridges, you should be knowing about what are AC circuits. What is an AC circuit? So you know that there are two types of currents: alternating current and direct current, AC and DC. See, AC circuit means these circuits, AC circuits, works by connecting AC source. The circuit that is excited using alternating source is called an AC circuit. The circuit that is excited using alternating source is called an AC circuit. The alternating current AC, the alternating current AC is used for domestic and industrial purposes. In an AC circuit, the value of the magnitude and the direction of current and voltages is not constant. It changes at a regular interval of time. In case of AC circuits, current keep on fluctuating, both in magnitude and direction. Whereas in case of DC circuit or direct current, there is no fluctuations or variation. Those circuits works by using alternating source or AC source, they are called AC circuits, and those circuits works based on the DC source, means direct current source. They are nothing but DC circuits. See, AC alternating current travels as a sinusoidal wave, completing one cycle as of positive and of negative cycle. So we can write the AC in a sinusoidal waveform. Okay, sine wave. So both keep on fluctuating, both the positive and negative cycle, and is a function of time and angle. Function of time t and angle theta equal to omega t. Omega is the angular frequency, t is the time, theta is the angle. Now, so as per your syllabus, AC bridges. So there are three AC bridges we have to discuss. See, before going to understand the AC bridges, construction and working of AC bridges, first we should be knowing about what is an AC bridge. See, AC bridge, those bridges works by using the AC source, alternating current source. They are nothing but the AC bridges. AC bridges are those circuits which are used for the measurement of unknown resistances, capacitance, inductance, frequency, and mutual inductance. AC bridges operate with only an AC source. Okay, whereas DC bridges operate with only a DC source. Okay. These AC bridges are very convenient and give the accurate result of the measurement. The construction of these AC bridges are very simple. See, AC bridge means you can look at the diagram here. Okay. One of the Wheatstone bridge is shown, is given. This is one of the AC bridge. If you observe here in AC bridge, in this given circuit, so you can see A, B, C, D. Okay. The bridge has 4 arms. AB is one arm, BC, AD and DC. So the bridge has 4 arms, AB, BC, AD and DC. And also you can see that the source, AC source, is connected between 2 nodes A and C. Between A and C there is a AC source connected. So that is the symbol of AC source. You can see there is a waveform. Okay. And there is a balance detector called headphone is connected between the remaining 2 nodes B and D. Okay. So between the A and C nodes, there is AC source connected, and the 2 remaining nodes, that is B and D. Between B and D there is a balance detector or headphone. Okay. Headphone is used as a balance detector which is connected between the 2 nodes B and D. So Z1, Z2, Z3 and Z4 are the 4 impedances connected between the 4 arms of the AC bridge. So generally here impedances of 3 arms are known and the impedance of remaining arm is unknown. Okay. So the condition for AC balance bridge is Z1 by Z2 equal to Z3 by Z4. So by using this condition, okay, that is given Z1 by Z2 equal to Z3 by Z4. So among 3 known impedances, other unknown impedance can be calculated. It works on the same principle as the Wheatstone bridge works. Wheatstone bridge works. Okay. The principle of Wheatstone bridge is used here. The null indication in the detector or headphone is obtained when the voltage at node B is equal to voltage at node D. Okay, if you measure the voltage at the node B and at node D, if voltages at node B is equal to the voltage at node D, then the detector or headphone H shows the null indication. Okay, that means headphone null indication in terms of we can measure the voltage, 0 voltage, or we can hear the sound also. Sound will be minimized or null, 0 sound we will get. We don't get any sound when bridge is balanced. Okay. Due to this, no current will flow through the detector or headphone. When bridge is balanced, no current will flow through the headphone. In such condition, the bridge is said to be balanced. Okay? When no sound will get then no current will flow through the detector or headphone. The condition is called the bridge is balanced. Okay, when bridge is balanced, no current will flow through the headphone. At the balance condition, current through the detector is 0 at the balance condition. Okay. So these are some important concepts about the AC bridges. Okay. And there are so many applications of AC bridges. Why we should discuss about the AC bridges? See, they have many applications. We can measure the inductance, we can measure the capacitances, okay, frequency, dissipation power factor, okay. So for different purposes, we can use the AC bridges. See here, if you learn the application of AC bridges, first point is, it is used for the measurement of inductances, L. We can measure the inductance, L. So there are so many bridges to measure the inductances. Anderson's bridge, Maxwell induction bridge, Maxwell inductance capacitance bridge, Hayes bridge, Owen's bridge, etc. Okay. So there are all different bridges used to measure the inductances. But as per your syllabus, Anderson's bridge and there is a Maxwell induction bridge. Okay. Anderson's bridge and Maxwell's induction bridge are mentioned in your syllabus. These bridges are used to measure the inductance. So, second application of the AC bridge is, it is used for the measurement of capacitances. Used to measure the capacitances of the given capacitor. Okay. Desortis bridge, Scaring bridge, etc. So Desortis bridge is mentioned in your syllabus. Okay. That is used to measure the capacitance of the capacitor, whereas Anderson's bridge and Maxwell's bridge are used to measure the inductance of the given inductor. And few more applications of the AC bridges are, it is used to measure the frequency. For example, Wayne's bridge, it is used for the measurement of, okay, AC bridges are used for the measurement of dissipation factor. And also AC bridges are used in providing phase shift and a feedback path to the oscillator. So these are all some applications. Okay. So we have many applications. So therefore, learning the AC bridges are very important in electricity. Okay. Now, so we'll discuss the AC bridges as per your syllabus. See in this slide, you can see that AC bridge is given. The Wheatstone bridge principle is applicable for AC bridges, is also applicable. Okay, there are so many bridges principle we can use. So generally, one of the important application is Wheatstone bridge principle. Okay, is used for AC bridges. So at balancing condition, when bridge is balanced, Z1 by Z2 equal to Z3 by Z4. Hence, the potentials at B and D are same, and this will be indicated by minimum sound in the headphone edge. Okay, we have discussed all this. Now, so there are three bridges mentioned in your syllabus: Anderson's bridge and Anderson's bridge, Maxwell's induction bridge, and Desortis bridges. So first one of the bridge is Maxwell's bridge. So in Maxwell's bridge, if you observe the circuit diagram, so you can see the four arms of the bridge. So A, B, C, D are the four nodes. Between A, B arm, R1 is connected. Between B and C arm, second arm B and C, R2 and C, resistance and capacitor C, both are connected in parallel. And third arm AD, between AD, inductor L and variable resistance, okay, R3 are connected in series. And fourth arm CD, resistance R4 is connected, okay. So here C and R3 both are variable. To bring the bridge to balancing condition by varying the value of capacitor C and resistance R3. Okay, we can, by varying the value of R3 and C, we can bring the bridge to balancing condition. There is an AC source which is connected between the across the nodes A and C. So this bridge, Maxwell's bridge, is used to measure the inductance L, which is connected between the two nodes A and D. Okay. This bridge is suitable for the measurement of inductance of a coil L. The bridge connections are as shown in the figure. The potentials at B and D are made same by adjusting the value of C and R3. Both are variable that you can see in circuit. Hence, the sound in the headphone becomes minimum. At balance point, Z1 by Z2 is equal to Z3 by Z4 as per the principle of Wheatstone's bridge. Z1 by Z2 equal to Z3 by Z4 that we have discussed in the previous slide. You can call it as equation number 1. For Maxwell's bridge, see, if you compare this bridge, Maxwell's bridge, with the Wheatstone's bridge, okay, in first slide. So in place of Z1, there is R1 here, okay, and in place of Z2 in Wheatstone's bridge, here R2 and C both are connected in parallel with each other, okay. Therefore, when the resistances are connected in parallel, then the effective resistance can be calculated as 1 by Rp is equal to 1 by R1 plus 1 by R2. Okay. Therefore, 1 by Z2 is equal to 1 by R2 plus 1 by Xc, where Xc is the capacitive reactance of the capacitor. So, by simplifying, see, Xc is nothing but 1 by J into omega C. Okay. Now, so by simplifying, 1 by Z2 is equal to 1 by R2 plus J omega C. Okay. And if you observe the Z3 in Wheatstone's bridge, in place of Z3, here in Maxwell's bridge, L and R3 both are connected in series with each other. Okay, in between the node A and D, L and R3 are connected in series with each other. Therefore, when two resistances are connected in series with each other, then the effective resistance Rs equal to R1 plus R2. Therefore, R3 plus J omega L. J omega L is nothing but the inductive reactance XL. XL equal to J omega L. That is the resistance of the inductor. Resistance of the inductor is XL is equal to J omega L. Whereas the resistance of the capacitor is capacitive reactance X equal to 1 by J omega C. Okay. And Z4, the fourth arm of the bridge, Z4 equal to R4. So, you have to compare the Maxwell bridge with the Wheatstone's bridge. Okay. Right. Then, substituting them, that is, substituting the value of Z1, Z2, Z3 and Z4 in equation 1, then we will get, so Z1 by Z2 equal to Z3 by Z4. In place of Z1, substitute R1. In place of Z2, okay, here we have 1 by Z2, okay. So, substitute the value for 1 by Z2 and Z3. Z3 means R3 plus J omega L and Z4 is nothing but R4, okay. And simplify, multiply the R1 value, left side of the equation. Then in right side also separately divide the numerator by R4. Then you will get equation 2. See here in this equation 2, real part and imaginary part. Okay, the term which is not having J, they are real parts or real terms. Those terms which are having J, they are the imaginary terms. So in equation 2, in left LHS, R1 plus R2 equal to R3 by R4. Okay, they are the real terms. Imaginary terms are J omega C R1 equal to J omega L by R4. So therefore, by equating the real and imaginary parts of equation 2, we will get for real terms, by equating the real terms, R1 by R2 equal to R3 by R4. You call it as equation number 3. And by comparing the imaginary parts, omega C R1 equal to omega L by R4 from equation 2. By cross multiplication, L is equal to omega will get cancelled. So L is equal to C R1 into R4. You call it as equation number 4. So equations 3 and 4, that is R1 by R2 equal to R3 by R4 and L is equal to C R1 R4. So equations 3 and 4 are the two balance conditions. The self-inductance of the coil is found using the equation number 4. To find the self-inductance value in case of the Maxwell's bridge, so to use the formula L is equal to C. C means capacitor. You can look at the terms in Maxwell's bridge. There is a C, variable C, R1 and R4. Okay, L is equal to product of C, R1 and R4. Okay. So if you know the value of C, R1 and R4, we can easily calculate the self-inductance value L by using the formula L is equal to C into R1 into R4. Okay. So these are the important points, circuit diagram and equations in case of Maxwell's bridge to find the inductance of the given coil. Okay. So this is one of the application of AC bridge to calculate the L. So in your exam, okay, there are questions, main questions, construct and derive an expression for the self-inductance of the given coil in case by using the Maxwell's bridge. Okay, there is one of the main questions, you can expect the main questions. Okay. Now another bridge, AC bridge is D-shortage bridge. Okay, D-shortage bridge. Yes. So D-shortage bridge is an AC bridge used to calculate the capacitance of a unknown capacitor. Okay, the value of unknown capacitance of the given capacitor. See, the circuit diagram of D-shortage bridge is shown. There are four arms of the bridge which are connected, R1, C1, R2 and Cx, which are connected between the four arms of the bridge. Between the A and B node there is R1, between B and C nodes there is C1. C1 is the capacitor. Okay. Between A and D, R2, resistance R2. Between C and D there is a unknown value of capacitor. Okay, which has to be find out. So Cx. Okay, we have to calculate the value of Cx by using the D-shortage bridge. Okay. C1, R1, C1, R2 known, Cx is unknown. Between B and D, nodes B and D, there is an headphone. Okay, there is a headphone connected in between the B and D. This bridge, this D-shortage bridge, is used to determine the capacity of an unknown capacitor. Okay, D-shortage bridge is used to determine the capacity of an unknown capacitor. It is connected in the fourth arm of the bridge, as shown in the figure. You can see the figure. Okay, so Cx is connected at the fourth arm of the bridge, and there is an AC circuit connected between A and C nodes. The values of R1 and R2 are adjusted. Okay, if you observe R1 and R2 in the D-shortage bridge circuit, both are variable. Therefore, we have shown the arrow. Okay, arrow mark for R1 and R2 that represents both are variable. R1 and R2 are adjusted until the sound in the headphone becomes minimum. Okay, by varying the value of R1 and R2, so you have to bring the headphone to zero sound or minimum sound. Okay. See, at balancing condition, Z1 by Z2 equal to Z3 by Z4. We know that. Okay, from the principle of Wheatstone's bridge, we know that the ratio of the impedances, first arm divided by second arm, is equal to impedances at the third arm by fourth arm of the bridge. You call it as equation number 1, Z1 by Z2 equal to Z3 by Z4. Here, see, we have to compare the D-shortage bridge, arms of the D-shortage bridge with the standard form of principle of Wheatstone's bridge. In place of Z1, here there is an R1. So Z1 equal to R1. In place of Z2, here there is a capacitor C1. So its resistance is 1 by j omega c, C1. Okay. Therefore, Z2 equal to 1 by j omega C1. In place of Z3, there is an R2. In place of Z3, there is a R2. And in place of Z4, there is a Cx, which is having the capacitive reactance 1 by j omega Cx. Therefore, if you substitute all these Z1, Z2, Z3 by Z4, okay, all these four values in equation 1, then you will get R1 by 1 by j omega C1 equal to R2 by 1 by j omega Cx. by simplifying and cross multiplication, by cross multiplying, here j omega get cancel each other. Okay. Then by simplifying, you will get R1 C1 equal to R2 Cx, or Cx equal to R1 by R2 into C1. Okay. So this is the formula used to calculate the value of unknown capacitor, unknown capacitance of the given capacitor by using the disordered bridge. R1 and R2 are known value, C1 also known value. Okay. So by substituting the value of known values of R1, R2 and C1 in a formula Cx equal to R1 by R2 into C1, you can easily find the value of unknown capacitor Cx. The bridge is also used to verify the law of capacitances. The law of capacitances means, suppose when two capacitors are connected, okay, in series with each other, C1 and C2 are capacitors which are connected in series with each other, then the effective capacitance is nothing but 1 by Cs equal to 1 by C1 plus 1 by C2. And when two capacitances are connected in parallel with each other, then Cp is equal to C1 plus C2, okay, which is reverse of the resistance law of resistances and law of inductances. Okay. Yes. So this question also you can expect in exam. Construct the disordered bridge and find or derive an expression for the capacitance of a given unknown capacitor. Okay, you can expect this question for the main question, as a main question in your exam. Okay, so therefore learn these both the bridges, Maxwell bridge and disordered bridge. In next class there is one more bridge, Anderson's bridge. Okay, so we will discuss Anderson's bridge in your next class. Okay, and we'll learn numerical problems also. Thank you.